You're fantastic. Thank you so much. Okay. Good afternoon, chemistry students. I just have to take a moment before we start and brag on my second-born son. All my kids have been taking some time last few weeks to learn new things, and my son Reed has learned how to make cappuccino. And this is like killer homemade cappuccino, and he is like very good at what he does. Okay, so I'm going to be talking a little bit today about the last of our first set of gas laws. And, okay, where did my other window go? Never mind. Just to kind of recap from yesterday, we had this goofy saying right here, my cup runneth over into my boot and my glove. This was a way for us to remember which gas law goes with which formula. Cup, of course, means Charles's law. In Charles's law, pressure stays constant. So if pressure stays constant, then we can see when temperature goes up, volume goes up, and when temperature goes down, volume goes down. So Charles's law was V1 over T1 equals V2 over T2. Boyle's law, temperature stays constant. And so if we keep temperature constant and we change volume or pressure, we see that the other one goes in the other direction. So Boyle's is P1 times V1 equals P2 times V2. And then Gay-Lussac's law, volume stays constant. So if I keep volume constant with my magic stick right here, I can see that temperature and pressure both increase together or decrease together. And so Gay-Lussac's law, I really don't know how to pronounce this poor guy's name, is that P1 over T1 is going to equal P2 over T2. Now, in each of these three cases, what we're assuming is that at least one of our variables, pressure, volume, or temperature, is going to stay constant. But what if you get in a situation where everything changes, where nothing stays constant? Well, then what we're going to have to do is we're going to have to derive a new formula that uses bits and pieces of all of these. And that's going to be the new knowledge for today. What we're going to be using now is what's called the combined gas law. And this is really nothing to panic about. We're literally taking these other three laws and we're combining them into a single one. And so combined gas law looks like this. Pressure 1 times volume 1, should be a 1, not an I, divided by temperature 1 equals final pressure times final volume divided by final temperature. And you are going to work problems using this exactly like you have worked problems using this before. You're going to look at a word problem, figure out what variables they give you, figure out what variable you're missing, rewrite the formula to get it in a more useful form for you, and then solve for whatever your missing variable is. So keeping in mind while we're looking through all this that anytime we use temperature, temperature must be expressed in Kelvin, or else the math just simply will not work. And again, you get Kelvin by taking degrees Celsius plus 273. Okay, very easy conversion. We just have to remember to do that. So I'm going to now refer to our gas law practice problems packet. Again, if you have any questions, jump right in there and stop me. I'm going to go to the third page, starting with number 12. Number 12 gives us one of those big tables. I think yesterday on one of the videos I freaked out a little bit because one of the numbers that I got working one of the table problems didn't seem to make sense to me. That's because I wasn't really thinking straight. It was something to a negative power. That doesn't mean it was a negative number. It just means that it was a very, very small number. And I should have caught that, and for some reason my brain was dead and I didn't. So trust your math, trust your calculator. I'm going to take another sip of my amazing cappuccino here. Hold on. Oh, God, that's so good. And get my calculator. And let's take a glance at problem number 13 here. Scientist has a sample of gas that was collected several days earlier. Sample has a volume of 392 cubic centimeters at a pressure of 0.987 atmospheres and a temperature of 21 degrees Celsius. On the day the gas was collected, the temperature was 13 degrees Celsius and the pressure was 0.992 atmospheres. So what volume did the gas have on the day it was collected? So let's take some clues from our thing here to see what it is they want us to find. They want us to find what volume did it have when it was collected. So on the day it was collected, what we're going to be looking for here is V1. So I'm going to list all of my other variables to see what I've got. And I have a feeling that I might need a little more space than what I've given myself on my paper here. So I'm going to cheat and I'm going to use my own scratch paper. That's not really cheating. It's, you know, using the resources that you have. Okay, so I'm going to start by listing out the variables that I have. Okay, I'm just going to go P1, V1, T1, P2, V2, and T2. Let me make sure I don't get that off the screen here. And so let's go through the problem and figure out what they've given us for each of these. As a sample that was collected several days earlier. The sample has a volume of 392 cubic centimeters. Now that, since it has that, now we're not talking about when he first collected it. So this is going to be final volume. So V2 is going to be 392. I'm going to go ahead and put units on here. It's not a bad habit to get into. At a pressure of 0.987 atmospheres, and so that's the current pressure, so that's going to be P2, 0.987 atm, and a temperature of 21 degrees Celsius. So temperature of 21 degrees Celsius, we're going to have to add 273 to that, so 273 plus 21 is 294 Kelvin. So I can ignore this 21 degrees Celsius part. On the day it was collected, the temperature was 13 degrees Celsius, so coming up to temperature 1, if it was 13 degrees Celsius, changing that to Kelvin by adding 273, that would be 283, 286. And the pressure was 0.992 atmospheres. So P1 is going to be 0.992 atm. We are looking for V1. When we find V1, it's also going to be in cubic centimeters. Okay, am I going too fast for anybody? Give me a wave or a thumbs up or something. We going all right? Okay. So now that I've got all my variables, I'm going to put up my combined gas law equation, which is P1 times V1 over T1 equals P2 times V2 over T2. Now I'm trying to solve for V1. So what I want to do before I start plugging in numbers is I would like to algebra these and get this to where V1 is all by itself. So I look to see what is up by V1. Right now it is being multiplied by P1 and divided by T1. So what I can do is I can multiply both sides of my equation by the reciprocal of just this part right here. So I can have both parts being multiplied by T1 over P1. And same thing on the other side, T1 over P1. Now, if you wanted to, you could also do those one at a time. You could multiply both sides by T1 and then divide both sides by P1. It does the same exact thing. But what that's going to let me do is it's going to let me cancel T1 and P1 on this side. So I'm left with V1 being equal to P2. Let me just bring this down here and rewrite it. V1 equals P2 times V2 times T1 over T2 times P1. Now I'll plug in all of the numbers that I have over here on the side. P2 is 0.987. V2 is 392. T1 in Kelvin is 286. T2 on the bottom in Kelvin is 294. And P1 was 0.992. Now, the easiest mistake to fall into at this point when you're putting this in your calculator is going to have something to do with whether the calculator thinks you're trying to multiply a number or trying to divide a number. Okay, so I like to keep with what I always say when you've got a whole lot of numbers in a big fraction like this. Everything on top here, I'm going to multiply by each one of those. Everything on the bottom here, I'm going to divide by each one of those. So when I put this in my calculator, I can put it in as all one big thing. I'm going to go 0.987 times 392 times 286 divided by 294 divided by, again, 0.992. And my calculator gives me an answer of 379.41. So I'm going to say that my starting volume is 379.41. And again, to check for what unit I need to use, volume is in cubic centimeters here. So I always want to be sure and include my unit with my answer. And that's how you work one of these. This is an excellent place for questions. So if anybody has one, you can yell at me in the chat, or you can put your hand up and I'll be happy to unmute you and hear what you have to say. Okay. You know, while I'm here, it's probably not a bad idea to work another one. And so I'm going to come back up to our table of problems up here. And I'm going to work one of these where I'm trying to solve for temperature, because something weird happens when you try and solve for temperature. And I want to show you what that is so that you don't fall into the trap. So I think what we're going to do is we're going to do problem 12C. Just flip my book over here. Problem 12C, we're solving for temperature number 1. And so if I write my combined gas equation, P1 V1 over T1 equals P2 V2 over T2, and I want to try and isolate for T1, after isolating, what I need to do is I need to divide both sides by P1 V1. If I divide both sides by P1 V1, then I'm left with 1 over T1 equals P2 V2 over T2 P1 V1. And here's where my problem is. Because right now, if I were to plug in numbers, and if I were to solve all of this, this right here would not give me T1. And I'm shocked. What it would give me is it would give me 1 over T1. And it's so super, super easy to forget that when you plug in all these things, it's not actually giving you what you want. So there are a couple of ways around this. You can intentionally rewrite this problem to put T1 up in the numerator by doing some more fancy multiplying and dividing, but I want to show you something else you can do because math says that it is perfectly fair to do this. Since this up here is a proportion, all of this is equal to all of this as a ratio of numerator to denominator, it is equally true for me to take this entire thing and invert it, which means that it's equally true to say that T1 over P1V1 equals T2 over P2V2. When you have equalities like that, that's fair game. It's going to give you, since this is just a ratio, this is the ratio that's inverted, it's still perfectly legal to do that. And so in this case, all I need to do from here to get T1 by itself is multiply both sides by this P1V1 here. Okay, I've kind of run myself out of room. Let me see if I can cheat. Put up some more paper here. So when I bring this down here and I multiply both sides by P1V1, what I'm left with is T1 equals T2 times P1 times V1 over P2 times V2. Now I know if I plug this in right here, it's going to give me the answer I need. Now comparing this to what I had a minute ago, what I had a minute ago is the same thing, it's just all flipped over. So you could also, and it would be perfectly fair to get to this point and just invert this whole thing and flip it over, and you get the same thing. It would be just like T1 over 1. So however you choose to rewrite that, at this point, since I've rewritten this, I can take the numbers that they give me and I can plug them in to solve for my missing T1. So T1 is going to equal T2. The T2 that they give me here is 293K. So 293 times P1, which is 0.029 atmospheres, times V1, which is 249 milliliters, divided by P2, which is 0.098, and V2, which is 197. My calculator got bored and went to sleep waiting on me to do something, so let me turn him back on here. Oh, that's some glare. So we're going to go 293 times 0.029 times 249, if I can read my own writing, divided by 0.098 divided by 197. And it gives me, for an answer here, 109.59. Now because this is temperature, and because they already gave me temperature in Kelvin, I'm just going to leave this in Kelvin and go up to my table up here and plug that in. So 109.59 K. Unless a question specifically asks you for a temperature in Celsius, I am fine if you leave every temperature in Kelvin. It's just, there's no point in converting it back if you don't have to. I want to show you one more cool thing you can do with the combined gas law, and then I will open it up for y'all to tell me where to take the discussion here. If I have my combined gas law, P1V1 over T1 equals P2 V2 over T2. I can use this to derive any of the other three gas laws we've looked at so far. Coming back to our magic stick right here. If I have Boyle's law, which one of these is going to stay constant? Well, I think Boyle's law, that's Boot. So for Boyle's law, temperature stays constant, which means if temperature is not changing, then you can just cover up the T's and look what you have. you have Boyle's law. P1V1 equals P2V2. For Charles's law, you think cup. So pressure stays constant. When I cover up pressure, I cover up pressure up here, and look, I've got V1 over T1 equals V2 over T2. It's Charles's law. Same thing with Gay-Lussac's law, okay? I think glove. Gay-Lussac's law, volume stays constant, so all I do is cover up my V's. I'm left with P1 over T1 equals P2 over T2. So this is really the only formula. If you're going to memorize one, memorize that one, because you can use it for everything. And with that, I am done talking. So I'm going to unmute everyone for just a minute, and if you have any questions about anything I've talked about today, you can let me have it, and then I can use however much of the rest of this time to just work practice problems with you if you want to stick around for that. So you are all unmuted now. Does anyone have a question? Okay, Dart has remuted himself. Okay. So I'm not hearing any questions out there. Go ahead and, well, I'll leave you unmuted if you want to stay unmuted, and you can either, oh, siblings, yeah, I hear you. I had a few of those myself. I actually still do. You know, I managed not to kill either of them, so, you know, that's good. So, you know, I've still got plenty of time on my hands here, and we've got lots and lots of practice problems to do on this gas laws thing, so I will go wherever y'all want to go. So somebody can either shout out a number and we'll go do it, or somebody can type a number in the chat and we'll go take a look at it. Sure, I've got my volume up where I can hear y'all. Or I can sit here and drink coffee in your direction. That's okay with me too. So good. When we get out of quarantine, you guys have really got to drag Reed, you know, and say, hey, make me a coffee, because, you know, he's very, very good at what he does. Between Reed making me coffee and Sadie making me bread, I am going to get so fat, you guys. Okay, nobody's saying anything. I don't want to waste any of your time. If you want to just work on these and then catch me later and ask me about them, that's fine. Okay, I'm counting down in my head from 10, and then I'm going to go ahead and end this recording. It does make pretty good sense. Once you can look through the problem and, you know, if you've got something where it gives you a table like this, that's not hard to figure out what's what. But if you can look through a problem and just figure out, okay, what do we start with and what do we end with? So you know which things are your ones and which things are your twos. After that, it's not hard. I put a, yeah, it is plug and chug. I like that. I put a YouTube video up by this kid who is both younger and better spoken than myself, that talks about how to pick the right formula for working a gas laws problem if you don't know. It makes for some pretty good watching. So y'all feel free to go check that out. It's in the Google class. Okay, then I'm going to go ahead and end the recording here. And if anybody wants to stick around after I hit stop and ask questions, that's fine. But everybody else watching this later, good luck on this. Don't be afraid to come get help.